Good afternoon, everyone. My name is John Suho. People call me John Suho. I am a senior security engineer in the Security Architecture and Engineering Group at InterSystems. Today, I'll be talking to you about data on the move, securing InterSystems IRIS connections with TLS. Part of the motivation behind this is the proposed change to the HIPAA Security Rule, which, if enacted, would require all electronic PHI data in transit to be encrypted and make it harder to get exceptions. But even if it's not legally required yet, you probably should consider it anyway. Our objective today is to help you understand what's needed to configure TLS for InterSystems IRIS and related processes. We'll ask, what does TLS protect against? Explain the problems of eavesdropping and impersonation, discuss the solutions of encryption and authentication, talk about what the TLS protocol is and how it provides these. We'll spend quite a bit of time talking about what files we need to set up TLS and how they work, which will help you remember what files you need. We'll discuss the different authentication scenarios of who authenticates whom. We'll talk a lot about certificates, both endpoint and CA, as well as private keys and how they work. We'll discuss how and where to configure TLS settings within InterSystems IRIS and briefly discuss other places it may need to be configured. Then, so you know different options for obtaining certificates, we'll discuss different kinds of certificate authorities, be they public, homegrown, or private commercial. Then we'll have a smattering of miscellaneous items, things that may be helpful for you as you're configuring TLS. And spread throughout, we'll emphasize the importance of coordinating with the other side when configuring a connection. We'll start with something you may be familiar with, the old story of Alice and Bob, but today for our purposes, Alice will be a specific Alice who conveniently happens to be in the public domain, and Bob will be a rabbit. So, Alice and Bob want to communicate. They're going to send messages to each other over a network, but communications in a network don't go straight from point A to point B. The network of necessity is made up of all sorts of intermediate nodes that messages have to travel through to get from point A to point B. This leaves them open to what are called man-in-the-middle attacks. This includes eavesdropping. Messages have to travel through intermediate nodes, so whoever controls one of them could just look at the message. There's also impersonation. Whoever controls an intermediate node could just stop the message, not send it to the next node, then reply back to Alice as if they were Bob. And if they wanted to, they could make a totally new message and send it to Bob, pretending to be Alice. Now, in real life, Alice and Bob are not just a girl and her bunny friend exchanging personal letters. They're web browsers talking to websites, exchanging passwords and financial information. They're health systems sending patient information back and forth. Eavesdropping and impersonation can be serious problems. And the solutions for this, first, encryption, where the sender scrambles the messages so that any intermediate nodes can't actually understand them. Only the intended recipient should be able to decrypt or unscramble them. It's like talking in a secret code or locking up the message so that it can only be unlocked by the intended recipient. But if you are talking in code, but you're talking in that code to the wrong person, that is still an issue. We need some method of authentication to verify the identity of one or both parties. That way, they can be sure that they're talking to the right partner before they set up the encryption rules at the start of each connection. Cool. So, what is TLS? What does it have to do with this? It stands for Transport Layer Security, and per that RFC, it allows client-server applications to communicate in a way that is designed to prevent eavesdropping, tampering, or message forgery. You might have heard of SSL, Secure Sockets Layer, which is just the previous name of TLS. The name was changed to appease various parties after the browser wars of the late 90s. If you see any version of the protocol that starts with TLS, like TLS 2.0 if you see any version of the protocol that starts with SSL, like SSL 2.0 or SSL 3.0, know that it is old and you probably don't want to be using it. Even note that TLS 1.0 and TLS 1.1 are officially deprecated. Your organizations will have to make your own security decisions, but it's probably not a good idea to be using anything other than TLS 1.2 and TLS 1.3. And because TLS is connection security, and your machine, system, or application will only be one side of that connection, if you want to use a particular version of TLS, but whoever's on the other side of that connection only supports an old version, that's something you're going to need to figure out together, hopefully by having them upgrade whatever's on their side. Failing that, they'll have to put in some sort of proxy. All right, once a connection starts, to secure it, the two sides will need to perform a TLS handshake. That handshake does the authentication if configured to do so and sets up the encryption. We are going to talk a lot today about the authentication part of the handshake, and not too much at all about the encryption part. All you need to know about that is that when the encryption rules get set up, the two sides are actually able to magically, using math, decide on those rules in a secure way, even though they're still talking in the clear at that point. Now, this may seem very obvious, but when you're planning to configure a TLS connection, it's important to know what is the client and what is the server, right? The server is going to be the side listening and waiting for a connection. Client's going to be the side that reaches out to initiate that connection. And you'll have to identify, from a TCP/IP standpoint, like what those are going to be. And do you control both sides of the connection? Is one of them outside of your organization? Again, you need to know that. Some very classic examples, right? A client, a web browser opening a random port, a web server listening on port 443. IRIS interoperability services and operations could be either TLS servers or TLS clients, depending on their specific class or component. The web gateway acts as a client that connects to an InterSystems IRIS super server process acting as a TLS server. The same with an ODBC client connecting to the super server. Once you figure out what your client and server are, you'll need to figure out what level of authentication is required. There are 4 different possible combinations. The client authenticating the server, both the client and the server authenticating each other, also called mutual authentication, or MTLS, the server authenticating the client. This makes no sense by itself, you're not going to see that, and neither the client nor the server authenticating the other. This is not secure, don't do this unless you're just playing around. You might think it always makes sense for both client and server to authenticate each other, and that is true much of the time. For example, if both client and server are specific interoperability components from different hospitals exchanging patient data, then it makes sense for the client to authenticate the server so they know they're sending data to that one right party, and it makes sense for the server to authenticate the client so they know they're only receiving data from that one right party. But what about a web browser connecting to a web server hosting a website? In that case, the browser would care a lot about authenticating the right web server to make sure it isn't a fraudulent website. But the website probably isn't going to care that if the client is a specific Firefox browser on a specific laptop, or a specific Safari browser on a specific phone. In fact, whoever runs the server probably wants as many different clients to be able to reach it as possible. So in that case, the most sensible authentication is probably just for the client to authenticate the server. Again, I've never been able to think of a scenario where it makes sense for a server to authenticate the client without the client also authenticating the server. If you can think of one, I'd love to hear it, but it just seems silly. Again, as for neither side authenticating the other, this would still give you encryption, but not authentication. So like we were saying before, you are talking in code, but you're not sure who you're talking to. Maybe you do this if you're just playing around on a system that does not actually need to be secure, but for some reason you need it to test some functionality with TLS. I would probably only do this if I'm playing on a system where both the client and the server are on my personal machine and the connection doesn't actually go over the network. Again, this is not a secure thing to do. Okay, so those are the logical scenarios. But the actual requirements for any connection should be decided by the security admins from both sides of the connection based on laws, policies from both organizations, and the judgment of each organization's admins. The reason that it's important to identify which party is the client and which is the server, and to figure out which authentication scenario is needed, is that this will determine what files you need when you actually go to configure each side. Some of these files are certificates. Certificates are used to authenticate a party during the TLS handshake. For our purposes, they are analogous to ID cards. Client or server certificates are referred to as endpoint certificates. Certificates are issued by certificate authorities, abbreviated as CAs, which in our metaphor are analogous to whatever entity creates the ID card, like a DMV or a passport office. There isn't just one passport office or DMV, there are many, and similarly there are many certificate authorities. Anything that might give out a certificate is a certificate authority. We'll talk more about that later. And just like DMVs or passport offices, when a certificate authority issues a certificate, they're supposed to check that the party requesting the certificate is indeed who they say they are. Certificate authorities also have their own certificates, referred to as CA certificates. These certificates can be used to verify that specific endpoint certs were indeed issued by particular security certificate authorities. And that's where the analogy breaks down a little bit. It's not like the DMV has its own driver's license that can be used to prove that other driver's licenses were really made by that DMV, but that is how CA certificates work. And when we say the client authenticates the server, that means that the client checks to see that the server's certificate was issued by a CA that the client trusts. They check that this ID really came from this trusted source. With that in mind, what certificates do you need configured on each side for each scenario? We only have time to look at that first scenario, the client authenticating the server, but that will teach us a lot. The spoiler, the server will need to be configured with a copy of its own endpoint certificate, and the client will need to be configured with a copy of the CA certificate from the CA that issued the server's certificate. So let's look at that in the handshake. Alice is our client, Bob is our server. The server will need to be configured with a copy of its own endpoint certificate. The client will need to be configured with a copy of the CA certificate from the CA that issued the server certificate. During the TLS handshake, the server will send its certificate to the client. Now that the client has the server certificate, they'll verify it using the CA cert they configured earlier. Again, we don't have time to walk through the certificates exchanged in the handshake for all of the other scenarios, but here are the general rules. The server always needs an endpoint certificate. The client only needs an endpoint certificate if the server is going to check it. And if the other side is going to check your certificate, they'll need the CA certificate that matches your endpoint certificate, not their own, which you'd be surprised how many people get that wrong, how often people get that wrong. Here's a chart with all of the scenarios. Here's that same chart visually, right? So again, if the client's authenticating the server, the client is going to need the CA certificate pertaining to the CA that issued the server's endpoint certificate, and the server is going to need its own endpoint certificate. If both the client and the server are authenticating each other, we'll need the same thing, right? The client needs the CA certificate from the CA that made the server's endpoint certificate, and the server will need its own endpoint certificate. But the client will then need its own endpoint certificate, and on the other side, the server will need the CA certificate from the CA that made the client's endpoint certificate. All right? We're not going to cover the other scenarios because they're silly. Because authenticating the other side requires configuring the CA cert in advance, when you are setting up this connection with whoever controls the other side, you may need to coordinate with the admins on that side to provide you with or point you to the right CA certificate. If you're setting up a dedicated connection for your system to communicate with another system, the admins who control each of those systems may need to do that together. If your organization requires mutual authentication, you can set up your side to authenticate that. If your organization requires mutual authentication, you can set up your side to authenticate their side. But you'll need to talk to the admins who control the other side to make sure that they do the same, because that can only be performed on their side. All right, now that we've discussed certificates, we can talk about the other necessary files, private keys, which solve the following problem. Certificates can be, and frequently are, freely distributed over the internet. Up until TLS 1.3, they were sent unencrypted in the handshake. So what's to stop our fake Bob, or even Alice, from just saving a copy of the certificate and using it later to impersonate Bob? Right? When we verify the certificate, the CA certificates only check that the certificates are valid. In our analogy with ID cards, that would be the same as proving the driver's license was actually issued by the DMV, but not checking whether it belongs to the person trying to use it. So how does the other side know that the certificate you're sending them actually belongs to you? In our analogy with ID cards, you would compare the photo on the ID with the person's face. That's pretty obvious, but let's break down exactly how that works. First, someone takes a picture of their face. They take something only they have and use it to create a piece of information that corresponds to it. Then they submit the picture along with a request form to the passport office. After the passport office verifies the identity of the person, then they'll make the passport and embed the photo, that piece of information derived from the person's face, into the passport. And they'll mail the passport to the person who requested it. And when someone needs to verify that passport belongs to the person, they'll compare the photo, the derived informational artifact, to the face, the unique thing that only the person who requested the passport should have, and the two should correspond to each other. It works similarly with certificates, but instead of a face, you start with a private key. This is a piece of cryptographic information, a long number that you generate for your system before you request a certificate. Then, once you have a private key, signified here by our big golden key, you can use it to derive a matching public key, symbolized visually here by the black and white picture of the key. Now, it's mathematically easy to derive the public key if you have the private key. But it's hard to derive the private key if you just have the public key. Similar to how it's easy to make a photo if you have access to someone's face, but hard to make someone's face if you just have access to their photo. So, once you've made the public key from the private key, you submit that public key to the certificate authority along with a certificate signing request, a CSR, and then the certificate authority confirms the identity of the requester, and then they'll create a certificate using the information in the CSR and embed the public key in the certificate before sending it back to the requester. So, how do public-private key pairs help authenticate? I'm going to intentionally use the word encode here instead of encrypt so as not to muddle this with the encryption we were talking about earlier, and pedants can yell at me later about that. But cryptographically, if you encode a value using a private key, you can decode it using the public key. Also true in reverse, but don't worry about that. So, if someone sends something in clear text, then sends it again, but encoded with the private key, if decoding with the public key, which you can get from the certificate, gives you back the original clear text, you know that whoever sent you that encoded value has the private key. And if you have the private key, that means you're the one who requested the certificate. Let's look at that within the TLS handshake. Before they exchange certificates, the client and the server send a bunch of random data, so you get some random original value, which the side doing the authenticating, in this case Alice, our client, saves off. Then they exchange certificates. The server sends its certificate down, from which the client is able to get the public key from the certificate. Then the side being authenticated, our server here, passes that original value through the private key to get the encoded value, which it sends to the other side, who can then decode it with the public key, which they pulled out of the certificate, and compare it to the original value. If it matches, that proves the other side has the private key and therefore is the entity to whom the certificate was issued. The takeaway is endpoint certs always need their private keys. So anywhere you configure an endpoint certificate, you must configure the matching private key. Now, you don't need the private key if you're configuring the CA certificate, because only the CA needs that. You're not the CA. We'll see later why they do. We can revise that chart from earlier to show that anywhere you have an endpoint certificate, you'll also need its matching private key. And then we have a visual copy of that as well. Note here that the private key for the client, in this case Alice, is the one that matches the client endpoint certificate, right? She should not have Bob's private key unless Bob wants her to be able to impersonate him, which would be bad. Okay. Since we're talking about key pairs, we'll now also talk about how they're used to verify the authenticity of the endpoint certificate. So, remember how CAs have their own certificates. They also have their own private keys and their own public keys. And those public keys are embedded inside the CA certificate. When an endpoint certificate is requested and the certificate authority makes it, before they send it back to the requester, they'll sign it. The CA will take the endpoint certificate info and they'll hash it. Then they run that hash through the CA's own private key. That encoded hash becomes the signature, which is embedded back into the endpoint certificate before it's issued to the requester. So, if someone takes the signature from the endpoint certificate and then runs it through the CA public key, which they can get from the CA certificate, they should get back the original hash of the endpoint certificate information, which you can also just get by hashing the information from the endpoint certificate directly. So, if you calculate the hash both ways and they both match, you know that the certificate was processed, the endpoint certificate was processed using the private key of the certificate authority, which only the certificate authority should have, meaning it is authentic. So, one, it's really important for a client or server with an endpoint cert to not get their private key stolen so they don't get impersonated. And two, it's even more important for a certificate authority not to get their private key stolen, because whoever steals that can just make and sign as many certificates as they want with whatever information they want in them. And anyone who's already trusting that CA certificate will trust these new malicious endpoint certificates. To reduce the risk and impact of that, commercial certificate authorities are usually broken into what are called root CAs and intermediate CAs. So the main key, corresponding to what we call the root CA certificate, usually doesn't sign endpoint certificates directly with their private key. Instead, they'll sign a small number of intermediate certificate authority certificates. And these intermediate CAs, also called subordinate CAs or issuing CAs, will be the ones that actually sign different endpoint certificates using their own private keys. Then the commercial certificate authority will keep their root private key, the one for the root CA, in a super secure environment where it's even harder to steal than normal, and hopefully it's hard to steal normally. All right? So if a CA key does get stolen, it'll probably be one of these private keys for the intermediate CAs. And again, hopefully the CA is well run and you can't even do that. But if it does happen, then all of the endpoint certs issued by that one intermediate CA will be compromised, not trustworthy anymore. But all the ones issued by the other intermediate CAs will be just fine. So it's a way to spread out and mitigate the risk. It is theoretically possible for there to be several levels of intermediate certificate, kind of like a turtles all the way down situation, but usually there will only be one. But I have seen a couple cases where there were two. And the takeaway for you is, well, what does this mean for configuring certificates? It means you need to have an intermediate CA certificate as well as the root CA certificate. Otherwise, if you miss one, then there's no way to know that your endpoint certificate is official and valid and authentic, right? And for your purposes, you'll just take both of these and put them into the same file when you're doing your configuration. So let's look at how we configure TLS settings inside InterSystems IRIS. This is a TLS configuration in InterSystems IRIS. Isn't it pretty? We'll go over each of these settings loosely in order. Also, it says SSL TLS. That's just for legacy reasons. I'll point out the settings that actually control the TLS versions later, and you'll see that by default in modern versions, there's no SSL in there. All right, first, the configuration name. This is just a string. You'll set this here, and you'll refer back to it in the settings for your class, component, TCP device, or whatever you want to use these settings with. The description is purely informational text. The enabled field, it seems self-explanatory. Type is going to be either client or server. They're pretty much the same with only some very tiny differences. So if you're a client, you're going to have a field called server certificate verification, and if you're a server, the field will be called client certificate verification. This is the important one. This is the field where you specify whether you want to authenticate the other side. Server configs have an option of request here. That's extraordinarily niche. You would instead just choose require. Request is super application specific, and I don't think you're going to use it for your purposes. Then the other important part, the field file containing trusted certificate authority certificates. That's where you would put the location of the file that contains your CA certs. Now, there's a special value you can put in here instead. If you want this particular connection to act like a web browser and be able to verify anything on the internet, instead of a file location, you can just specify the string %OS certificate store. This will make it so that the connection uses your operating system's certificate store, which is pre-configured with hundreds of commercial publicly recognized certificate authorities, so that anything you'd expect to reach on a web browser, you'll be able to reach on that connection. But only do that if that's what you want. If you're expecting to reach one specific partner who's going to have one specific certificate that was issued by one specific certificate authority, why would you want to recognize hundreds and hundreds of them? That seems silly. But if that is what you want, go ahead. But know what you're doing. Don't just put in stuff until the connection goes through. All right, there's a section called this client's credentials or this server's credentials. This is where you put your own certificate and key. For server configurations, this will be required since servers always need an endpoint certificate, and anywhere you put an endpoint certificate, you also need a private key. For clients, this isn't required, but you will need to fill it out if the other side is is expecting to authenticate you. There's these radio buttons for private key type. That's just the algorithm that the keys use. The vast majority of the time, this will be RSA. I have never seen anyone use DSA. Starting with IRIS 2025.2, we're introducing support for ECDSA, which is starting to become a thing. Then there's the password field for the key, since the key itself is hopefully password protected. Having a password on the key would significantly slow down someone who has stolen it before they can use it, which would give you time to get your key and certificate replaced. Cryptographic settings include which protocols are enabled. Make sure you have the old ones disabled, especially if you've upgraded your system from a very old version where they may not have been disabled by default. There's also the cipher list. This is a list of the allowed algorithms in the handshake. There's a bunch of different parts to the handshake and different algorithms for them. Now, if you have certain policies where you need to disallow certain algorithms, you can configure that here. The most common reason to do this is to only use algorithms with what's called forward secrecy. Now, forward secrecy, or perfect forward secrecy, means that your encryption algorithms are not deterministically tied to your private keys, because some of them are. And that means that if you have only allow algorithms with perfect forward secrecy, that if someone is recording your traffic and they were to steal your private key later, then they couldn't, because there's no connection between the algorithm used to encrypt the traffic and your private key, that means they won't be able to just read them if they steal your private key. But there are some algorithms where they can. You'll see here that there's a separate field for enabled cipher suites just for TLS 1.3, and it's separate in part because TLS 1.3 has a different algorithm format which is in part because all of the algorithms in TLS 1.3 require forward secrecy. All right. OCSP stapling is advanced, and I have a whole video about it from 2020, so you can find that. Okay, so you've set up a TLS connection, but now you have to associate it with the settings for whatever's going to use it. You'll have to check the documentation for whatever specific class, component, feature, etc. to see where you put the name of that TLS configuration. For example, in this onslib HTTP service interoperability component, in the component connection settings, you'll find a field called SSL configuration. Again, that does not mean we're using any SSL versions. It's just, a class that's been around a while. We saw before that there were no SSL versions enabled. So you just put the name of your configuration in there, and then when at runtime, it'll use those settings that you made. Quick aside for things that are HTTP request based, like this interoperability component or like the %net.http request class, they have a setting called SSL check server identity. That is enabled by default, and you should leave it enabled. We don't have time to cover it in depth, but this is another check that we do. To take it back to our ID card analogy, so we checked to make sure that our certificate was issued by a trusted CA. And then we checked to make sure that whoever sent us the certificate actually has the private key and is the owner of the certificate. This is saying, okay, let's check the name on the certificate to see if it matches the server that we're trying to connect to in our connection settings. So in our ID analogy, it's the same as checking the name on the ID in addition to checking that the ID is real and in addition to checking that it belongs to the person trying to use it. It only exists for HTTP request-based things because those are clients, and clients have a field for something they're trying to connect to. Servers don't work that way. IRIS-related items that exist outside of the instance, like a web gateway or one of the ODBC clients, they're going to have very similar TLS settings, but they're going to be configured differently, like in INI files or like here through the web gateway management page, right? Everything's going to have very similar settings. This is true of things that are not necessarily IRIS, like Java processes that get kicked off by an instance but which are not IRIS processes. They'll have a Java config file where you set up Java key stores and things like that. And of course, web servers, classic example of something that you'll need to set up TLS for. You may also have network devices that sit in front of your web servers that need to be set up with. Anything that uses TCP and is not using a protocol where the encryption and authentication are built in, like SSH or SFTP, you're going to want to use TLS with it. At this point, I want to throw out this acronym, which describes the whole ecosystem of getting and using certificates. Public Key Infrastructure, PKI, a set of roles, policies, hardware, software, and procedures needed to create, manage, distribute, use, store certificates. And I do that because in order to actually configure TLS, we need to know where to get certificates from. I want to point this out. To make certificates, all you need is a CA private key. You use that to sign the CA cert and any other certs. But that key is just a big number in a file. And you can generate that with a tool like OpenSSL. And then you can use that same tool like OpenSSL to make any sort of cert you want. That's just math. That part isn't hard and it's not special. What's hard and what's special is the infrastructure to get the requests made and processed. And especially the roles, policies, and procedures you need to keep the private keys private. All right, let's use another analogy here. So far, we've been talking about the DMV or the passport office like those run by big governments. In real life, these are big, official, and pretty universally recognized providers of IDs. If you get an ID from there, you can use it at the airport, at the bank, pretty much anywhere. But there is nothing stopping you from just making your own ID cards in your garage. And if someone says, yeah, I'll recognize ID cards made by this garage, there is nothing stopping them from doing that. And then maybe there's something in between. Maybe you have a work ID issued by your company, and that ID card might work in your building, or a couple of different buildings administered by your company. It could be your company came up with their own solution for ID management, or maybe they're partnering with an entity that specializes in ID cards. All right, so we have these three different options. And regardless of who's making and managing the IDs, if they're not able to protect the means of making those IDs, that's a problem. Whether it's you in your garage or suddenly maybe the DMV is doing a bad job of controlling that machine, that's a problem either way. Okay, so corresponding to our passport office or DMV would be public or commercial CAs with wide recognition. These are things that web browsers would definitely trust. If you're going to need your cert to be verified by something out on the open internet, you'll probably need something like this. There's a lot of commercial CAs. I won't mention any of them in particular. Usually your hosting or your cloud provider might offer certs either from themselves or a third party. And secret managers are also a potential certificate supplier. And they're good at keeping things secret. Corresponding to just making them in your garage, you, even as an individual, can just use OpenSSL or some other tool to make a CA cert and key pair and then issue certificates. Windows Active Directory certificate services can also be used to generate a CA key and cert and then request and issue certificates. And in order to use these certificates, you would need to give the CA cert you made to the parties that would need to use it, right? Commercial CAs, you can get those online. Nobody's heard of your garage. Here's the kicker here. You need to be responsible for making sure that the CA key doesn't get compromised. Do you have the infrastructure, policies, and procedures to make sure the CA keys stay safe? Maybe. But if not, maybe only do this in play environments that don't actually need to be secure. Moving on to our in-between case in the analogy, an ID that is recognized by a workplace or a set of workplaces would be a private CA. Maybe it's a homegrown CA that grew to be very sophisticated, or more likely, there are companies that you can, hire to help you run private CAs that make your tooling and request process easier, right? These again could be just your cloud or hosting provider or a company that specializes in certificate management. And these can be a nice intermediate where you need more structure in managing certs in a private environment. But again, as always, just make sure the private keys stay safe. So those are all the different kinds of solutions for CAs, but I will name one special public CA. It's not a commercial CA, but it is public and it's free. It's called Let's Encrypt. It was started by the Internet Security Research Group just to make it easier for people to use TLS. They also developed the ACME protocol for automation, which is going to be increasingly important because over the next few years you're going to have to replace your certificates more often. Like ID cards, certificates have expiration dates. And like ID cards, with certificates and keys, the longer that the expiration date is set, the longer a malicious actor can abuse the certificate if they get hold of the key. Right now, the max lifetime on a cert that's recognized publicly on the internet is going to be about 380 days. Over the next 4 years, that's going to shrink down to 47 days. So you're going to need to renew your certificates a lot more frequently. Some miscellany. There's a super duper subset of homegrown CAs called self-signed certificates. Sometimes people use self-signed certificate to mean, well, okay, this came from a homegrown CA. That's a valid usage, but there's a more specific one. To be pedantic, there are some homegrown certificates where the CA cert and the endpoint cert are the same cert. It's like a Franken-cert. It's like the passport and the passport scanner are welded together. This is definitely not something trustworthy for the public internet, but it's something you should know about. We need to have a brief word on certificate and key formats. Most importantly is the PEM. That's the base 64 encoded format. This is what InterSystems IRIS uses. This is also what Apache uses. It's going to look like dash, 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 begin certificate, and a bunch of ASCII letters. If you open up your certificate in a text editor and you don't see something like that, you're in the wrong format. There's binary encoded formats, DIR. There's PFX and PKCS12. This is a format where the cert and the key are in the same file. So if you have one of those, be careful to not, send someone your private key when you're thinking you're just sending the certificate. And you can use tools to convert between these. Or you can Google these, but I'm just going to tell you things that you should Google. How to dump a certificate as a human readable text. Again, how to convert between formats. How to check whether certificate chain is complete, that it has all the root and intermediate certs for a given endpoint cert. And how to check the modulus in a private key matches the modulus in endpoint certificate. Because if you use a cert with the wrong key, that's not going to work. To recap, intermediate nodes might be dangerous, so we need encryption and authentication. TLS uses CA and endpoint certificate and keys. The side being authenticated needs to have an endpoint cert and key configured. The side authenticating the other party needs the matching CA cert. Coordinate with whoever controls the other side. Maybe not for the open internet, but most of you all are going to have a dedicated partner. Protect your private keys. Create a TLS config and then assign it in your processes settings. You can get certs from public CAs, homegrown CAs, or commercial private CAs. Which brings us to the end. I hope that even though we've gone down a bit of a rabbit hole, and though it may seem mad that these new encryption rules could be coming so soon, you haven't run out of time yet, so don't lose your heads. Just take a good look at yourselves and the current state of your environments, and smile. Thank you.